Here in this talk, I'm talking about the Chebyshev's bias, which is an unsolved mystery in number theory since the 19th century. This is a joint work with Nobushige Kurokawa. So let me start by explaining what is Chebyshev's bias. Chebyshev in 1853 pointed out that it seemed that most of the time there are more primes of the form 4k plus 3 than of the form 4k plus 1 up to the same bound. So put the bound to be x and count the number of primes less than x, which are congruent to A modulo Q. Then this inequality, pi x 43 is greater than or equal to pi x 41. This equality holds for this huge numbers of x. For this long interval x less than 26,861, this inequality always holds. If this is a competition between team 3 against team 1, then team 3 is always stronger. Team 3 is in the lead in this long interval. And then 26,861 is the first prime number when the opposite inequality holds. Team 1 leads for an instant, but it is just happening only for an instant, and immediately after that, at the next prime number, the equation holds and team 3 catches up. And then at the next prime number, 879, then the opposite inequality holds again. Then this inequality holds, and team 3 gets ahead. And after that, surprisingly, this inequality holds until over 616,000. So it's a huge interval. So during this huge interval, team 3 maintains a lead. So it seems that pi x 43 is greater than pi x 41 more often than not. So apparently there exists a bias towards primes of the form 4k plus 3. In other words, a bias against the primes of the form 4k plus 1. So this phenomenon is called the Chebyshev's bias, and it is a famous unsolved mystery in number theory, which is also in Wikipedia. In Japanese, it is called Chebyshev no katayori. Conclusion of this talk. At the end of this talk, we will know that Chebyshev's bias is a natural phenomenon. At first sight, it seems very unnatural, but it's a natural phenomenon in the sense that it is making a well-balanced disposition of the whole sequence of primes. And what do I mean by balance here is explained in the next line. The balance means the convergence of the Euler product at the center. So we'll consider Euler product in the critical strip, especially on the critical line at the central point, half. Then the convergence of the Euler product is equivalent to the Chebyshev's bias. That's what we'll reach. So the number 3 Chebyshev's bias is equivalent to the convergence conjecture. So this asserts that the Euler product converges at the central point, and it is a part of the deep Riemann hypothesis, which was proposed by Kurokawa 2012. So in this talk, we are only interested in whether or not the Riemann hypothesis is deep. So we are not interested in the generalized Riemann hypothesis. So we don't use the word GRH. So throughout this talk, GRH is abbreviated to RH. So we will just use DRH and RH. So here's the picture of DRH. Let me start from the Riemann hypothesis, which everybody knows. It asserts that zeta or L functions are non-zero in the critical strip. That means the real part of S is between 1/2 and 1. And then we will change the expression a little bit. We can change the expression into that in terms of the Euler product. If the Euler product converges in this region, then by the definition of infinite product in complex analysis, if an infinite product converges in some open set, then the limit is not zero. So then by this definition, this conjecture implies the Riemann hypothesis. So this is a little bit stronger than the Riemann hypothesis. But once we rewrite the Riemann hypothesis like this, then we can naturally extend the convergence region to the boundary. So now we attach the equality here. So and this conjecture is called the convergence conjecture. And this is the essential part of the deep Riemann hypothesis. The convergence conjecture asserts that the Euler product converges in this region. I should mention that this is the case of entire L functions. So we are thinking of the cases when the L functions are holomorphic at S equals 1. So like the Riemann data function, when the L function has a pole at S equals 1, then the Euler product obviously diverges in the critical strip. But in those cases, we need some modification. So, but in this talk, we are just dealing with the entire case. So the Euler product converges in the critical strip. And then the convergence conjecture is essentially equivalent to Chebyshev's bias. So this is what we discovered in this talk. So this would be the main theorem of this talk. And then it is naturally implied by the deep Riemann hypothesis, because deep Riemann hypothesis is a stronger version of the convergence conjecture. It says not just the Euler product converges, but also it expresses the L values. So of course, this implies the convergence conjecture. So the deep Riemann hypothesis implies the Chebyshev's bias. Chebyshev's bias has never been formulated or never been defined so far. So in this talk, we will do that for the first time. This is the history on Chebyshev's bias. The first traditional result was proved by Littlewood, 1914. The difference changes its sign infinitely many times. And then the Nepomsky-Tran conjecture was proposed in 1962. It's a natural conjecture saying that the natural density of the set AX, where the team 3 is stronger than team 1, this interval goes to 100% in the whole positive numbers. It seems that this conjecture is very natural, but unfortunately, it was proved to be false under the Riemann hypothesis. This limit does not exist. Then in 1994, Rubinstein-Sarnak proved that if we replace the natural density with the logarithmic density, then the limit exists. The definition of the logarithmic density is like this, and they proved that the limit is very close to 1. It is more than 99%. And this would express the Chebyshev's bias. That's what they thought. But unfortunately, they needed some assumptions. The Riemann hypothesis and Li is the linear independence hypothesis. And this Li is a very hard conjecture. It is far beyond our reach. Linear independence means that the imaginary part of zeros of zeta functions are linearly independent over Q. So this is a very unrealistic assumption, very hard, much harder than the Riemann hypothesis, and it is very unrealistic. But under these assumptions, they found this type of truth. So, and after their work, it is considered that this theorem is epoch-making. So, and many papers were published along this line. But in this talk, I am proposing a completely new method, which is very different from them. So we don't use any logarithmic density, and we don't use any linear independence hypothesis. Here is another reason why the Riemann hypothesis is insufficient for attacking Chebyshev's bias. This is the prime number theorem in arithmetic progressions by Dirichlet. Dirichlet's prime number theorem. That is pi x qa is asymptotically equal to this thing. So this is the main terms in prime number theorem. And Dirichlet proved that this doesn't depend on A, at least for the main terms here. So you just multiply 1 over phi q to these main terms for obtaining pi x qa. But of course, you have some error terms here. These are very small. And when you think of the difference for considering Chebyshev's bias, then all these things are canceled. So you have to consider the difference of the error terms here. But unfortunately, these error terms are very hard. These depend not only on rho, but also A. So it depends on A. So knowing the real part of zeros, which means the Riemann hypothesis, but the Riemann hypothesis is not enough for attacking Chebyshev's bias. So that is why Rubinstein and Sarnock assumed the linear independence hypothesis, that is very hard conjecture. And in this research, we will assume the deep Riemann hypothesis, which is instead of the linear independent hypothesis. This picture is for explaining the set AX is not good for attacking the problem. Assume that this inequality holds for the first 100 primes. In this interval, it is known that team 3 is stronger, but if we have this information, then you still have some possibilities. And then here are two extreme cases where this inequality holds in this long interval. The first case is the first 50 members are from team 3, and then 50 members are from team 1 later. So everyone from team 3 comes first, and then after that, team 1 comes up. So in that case, this inequality holds, but the difference becomes 50 at the maximum. On the other hand, if both teams appear alternatively, then team 3, team 1, team 3, team 1, team 3, team 1. And in this case, still this inequality holds during the whole interval. But this difference goes to just 1 at the maximum. So these two very different cases cannot be distinguished by just considering AX, even if we know that the whole interval less than the 100 prime are contained in AX. Still, we cannot distinguish cases 1 and 2. So obviously, the length of the interval does not lead us to the truth. So this is not enough. So we need some new method of estimating the difference. That is the motivation of this work. So here's the key idea for attacking Chebyshev's bias. The background is the prime number theorem in arithmetic progression. Team 3 is as big as team 1, so the number of elements are the same. Then we will reinterpret Chebyshev's bias. We regard Chebyshev's bias as follows. There seem to be more members in team 3. It seems to be true, but it is restated as members in team 3 appear earlier. Yeah? So since the number of elements are the same, so the problem is the timing of appearance of primes. So we reach our main idea. In order to regard smaller primes as heavier elements, we adopt a weighted counting function pi s instead of pi. So pi s is a generalization of the usual counting function pi. It is a sum over primes, but instead of adding 1, we are adding 1 over p to the s, where s is a non-negative real number. When s equals 0, of course, it is the usual counting function. But when s is positive, then we regard smaller primes as heavier. So we will use this generalized weighted counting function to have our main results. So here are the list of our main results. Everything is under the deep Riemann hypothesis for characteristic 0. But when the characteristic is positive, we already proved the deep Riemann hypothesis. So the theorem holds unconditionally. Denote by AS the difference between pi sx43 and pi sx41 is positive. So the team 3 is stronger in view of pi s. So by using this notation, we can prove that the density, the natural density of A half is equal to 1, so 100%. More precisely, we have the following identity. Pi s x43 minus pi s x41 is asymptotically equal to 1/2 times log of x as x goes to infinity when s equals 1/2. And when s is greater than 1/2, this difference is bounded. And we think that this is a new formulation, new and the first formulation of the Chebyshev's bias towards team 3. So it means that the team 3 is stronger because it is always positive as x goes to infinity. So it shows that the team 3 is stronger. So this is a bias towards team 3, and in other words, bias against team 1. And this theorem is proved by very simple calculation from the Euler product. Since the proof is very simple, we can use the same principle to various zeta functions. So, for example, we obtained the Chebyshev bias against splitting ideals in an extension of global fields, or the Chebyshev bias against principal ideals in the global fields of class number 2. I will explain it more details later. These are joint works with Miho Aoki and Shimane University. And these results are in algebraic number theory. So we gave a talk on it last month in the conference in Zurich about algebraic number theory. And here's the main theorem of today's talk. Since this is a conference of automorphic forms, we are looking at the Ramanujan's tau function. Ramanujan tau p has also a Chebyshev's bias to being positive. So that's what we will be proving later in this talk. And also here's an additional result. When we apply the same principle to the L function of elliptic curve, then we can get the Chebyshev's bias of AP. AP is the coefficient of an elliptic curve. And this result is under, not just under DLH, but we have to assume the Burton and Dyer conjecture. Anyway, I will talk about these topics from now. First, I will explain what the deep Riemann hypothesis is. It is a precise form of the deep Riemann hypothesis. Let K be a global field, and we think of the L function for a Galois representation rho. So it is defined by the Euler product. And the Euler factor is in terms of the Frobenius operator. Here, and V is the norm of the finite place. And then the deep Riemann hypothesis asserts that this limit holds. Here, M is the vanishing order at the center, and it is usually equal to 0. So we have a vague, not a clear conjecture, but we have a vague principle that it is called the non-vanishing principle, that the L functions are not 0 at the center. So in most cases, M equals 0. So when M equals 0, then this left-hand side is just the Euler product at the center. And as x goes to infinity, then when M equals 0, the denominator is 1. And this is just the ordinary value, special value of the L function at the center. So essentially, the Euler product expresses the special value of the L function, but you have to multiply this factor, square root of 2, to some power. This power is defined like this. It's an integer. It's a difference of the multiplicity of the identity representation contained in the symmetric square of the representation and the exterior square of rho. So anyway, you need this type of factor. Essentially, the Euler product expresses the L value. And when M is positive, then you have this factor, and then this goes to infinity. And so this factor must go to 0. So in those cases, when M is positive, then L function has a 0. So the Euler product goes to 0. So in any case, the deep Riemann hypothesis implies that the convergence conjecture, which is the Euler product converges at S equals 1/2. This convergence implies the converging to 0. The limit may be 0 at the boundary, 1/2. So this is the deep Riemann hypothesis. And when we restrict to the case of Euler's L function, this is the simplest case. And it is related to the Chebyshev's original case. The Euler's L function is defined by the Euler product over all the primes. Here, chi is the Dirichlet character modulo 4. So in this case, M equals 0 is known. So the deep Riemann hypothesis is equivalent to this red line. the Euler product converges, so its log converges to some constant L, and here L is expressed like this. And then we can expand by using the Taylor expansion of log. Then you have 3 parts here, and the third part, k equals greater than or equal to 3. This part is the easiest to handle, the third term. It is absolutely convergent since k equals greater than or equal to 3. So then k over 2 is at least 3 over 2. So then it is bounded trivially by the special value of the Riemann zeta function because it is in the absolutely convergent region. On the other hand, the first term, k equals 1, this term is expressed by definition. It is equal to pi half x for 1 minus pi half x for 3. And the remaining part, k equals 2, this may be the hardest part. In this case, chi p is a real character, so chi p squared is always 1. So for estimating this, you need the Euler's famous theorem, the sum of 1 over p over primes p less than x is asymptotically equal to log of x. So we can have the all asymptotics of each term from both sides. Then from all these things, we have the conclusion of Chebyshev's bias. Pi half x for 3 minus pi half x for 1 is asymptotically equal to 1 over 2 times log of x as x goes to infinity. So this is the proof, essential part of the proof of the Chebyshev's bias, and we can just define that this is the Chebyshev's bias. And the deep Riemann hypothesis is proved over functional fields. So as I told you earlier, we proved it last year, Kaneko, Krukava, and I. So when k is an algebraic function field of one variable, when the characteristic is positive, then DRH holds for any automorphic L function over GLN. So in a very general setting, DRH is known when the characteristic is positive. So I will give you many theorems in this talk from now, but all of them, in most of them, I will say under DRH. But that means the following. In the case of characteristic 0, then the theorem holds under the assumption DRH. But in the case of characteristic positive, the theorem holds unconditionally. So now I am introducing some preceding results, which I gave a talk last month on abelian extension. It is a joint work with Aoki. Let K be a global field and let L be a finite extension of it. Then denote by pi sx sigma is sum over primes. Here its absolute, its Frobenius element, the corresponding Frobenius element is equal to sigma. Sigma is an element in the Galois group. So by putting this, we can have the generalization of Chebyshev's bias. This is a generalized version of Chebyshev's bias to abelian extensions. So under the deep Riemann hypothesis, this type of difference is behaves like this. So here, tau and sigma means that tau is a non-square element in the Galois group, and sigma is a square element in the Galois group. So by comparing this, M is like this, and M is usually 0. So when these things are 0, then you have a positive constant here multiplied by log of x. So usually tau is stronger than sigma. So we have a bias against squares, and we have a bias towards non-square elements in Galois group. And Chebyshev's original case is restored by choosing the cyclotomic fields as an abelian extension. So when k equals q and L equals q zeta q, then the Galois group is isomorphic to the multiplicative group of the cyclic group. Then the squared element corresponds to A, which is a square in this group. So that is what we say quadratic residue. And the non-square element in the Galois group is corresponding to quadratic non-residue. So by an easy application of Theorem 1, we can naturally have the following corollary. So it is a comparison between non-square elements and the square elements, and the difference of pi half is equal to log of x, and with some positive constant. Of course, Chebyshev's original case is restored by taking QAB equals 4, 1, and 3. Then in this case, this coefficient is equal to 1/2. And also when both A and B are quadratic residues, or both are non-residues, in those cases, there are no bias. That's what we did. Example, modulo 8. When we consider modulo 8, then you have 4 possibilities, 1, 3, 5, and 7. And 1 is quadratic residue, and the other 3 elements are quadratic non-residue. In this case, 3, 5, and 7 are stronger than 1. So there's a bias towards these elements, 3, 5, and 7. So the difference goes to infinity as x goes to infinity. But for any pair of 3, 5, and 1, they have no bias. They are tied. Here's another corollary for the positive characteristic cases. Let f be a polynomial over a finite field, and then we can think of an analog of Dirichlet L functions in the positive characteristic cases. So for this quotient ring, you can have the invertible element in the ring. So from Theorem 1, you can easily have the following corollary. That is the difference between quadratic non-residues and quadratic residues. And it is also going to log of n with some positive constant. So this is the bias in irreducible polynomials over fq towards quadratic non-residues. For example, when q equals 2 and f equals t squared, then you have just 2 possibilities, 1 and t plus 1. Then the bias is towards t plus 1 because this is a quadratic non-residue and 1 is a quadratic residue. So if you have a sequence of irreducible polynomial ht, then there's a bias towards polynomials with a1 equals 1. It means that the polynomial having a linear term will appear earlier than those without the linear term, a1 equals 0. So since this is a positive characteristic case, we already have the DRH. So example 2 is proved without any assumption. So this may be a new phenomena which we discovered. We also have bias against splitting primes. when we think of general finite abelian extensions, not just the cyclotomic fields, then in a more general setting, we know that the Frobenius element is equal to 1. This is equivalent to that the prime ideal P splits in L. So by using this equivalence, we can have the difference between non-splitting and splitting. D means decomposing, but it's the same as splitting. So we can also estimate the difference between non-splitting and splitting. And non-splitting ideals are stronger. So under the deep Riemann hypothesis, we can have the bias towards non-splitting primes. Of course, now I am assuming for simplicity that L is a quadratic extension, and it is the easiest case. But we did prove for a general abelian extension, which would be more complicated form. But here I'm restricting for illustration. So there is a bias towards non-splitting against splitting primes. When we take the extension as the Hilbert class field of K, then in that case, the Galois group is isomorphic to the ideal class group. So in that case, we can compare the principal ideal and the non-principal ideals, and we can prove a bias against principal prime ideals. So this is all these things are joint work with Aoki, and they are results in algebraic number theory. Here's the main theorem today. We show that Ramanujan's tau function has a bias to being positive, where the tau n is defined like this. This is the Ramanujan's delta function, and the tau n is the coefficient of q to the n. And this is the Ramanujan conjecture, which is already proved. So we know that the tau n is between -2 times p to the 11 over 2 and 2 times 11 over 2. And Ramanujan defined the L function Ls delta. This is the L function having a functional equation between S and 12 minus S, and S equals 6 is the center. If we put the S plus 11 over 2 here, this is a normalized version of the Ramanujan's L function. So it has the functional equation between S and 1 minus S, and the center is at the S equals 1/2. So we can think of the deep Riemann hypothesis of this normalized Ramanujan's L function. And by under this assumption, we proved that it holds that tau p over p to the 6, the sum over this over primes less than x, is asymptotically equal to 1/2 times log of x as x goes to infinity. So this means that tau p has a bias to being positive here. So originally the tau p is in this interval, and we do not know the general tendency of the signature. I mean, we have the Sato-Tet conjecture. So in some sense, it is distributed uniformly. So the distribution of the Satake parameter is uniform in the sense of the Sato-Tet conjecture. So it is uniform for the first sight, but the bias means that more detailed things, more subtle conception. The Sato-Tet conjecture is what we can say is corresponding to the prime number theorem in arithmetic progression. So it is just counting the number of primes. But we are not just counting the number of primes. Based on the numbers are the same or the uniform, still we have a bias that is the timing of appearance of primes. So in that sense, tau p has a bias to being positive. This is our main result. And this theorem is extendable to a bias of general Satake parameters for automorphic representations of GLN. So it can be generalized to a very widely generalized situations, but the paper is not ready. Now I'm giving proof of theorem 4. We put tau p is 2 times p to the 11/2 times cosine of theta p. Here, theta p is the Satake parameter, and it is between 0 and pi. And MP is the unitary matrix corresponding to tau p. And then the normalized L function is defined by this Euler product over primes. The Euler factor is expressed as the determinant 1 minus MP, p to the minus s to the minus 1. Then the basic idea is the same as what I explained earlier for the one-dimensional case. Even if we have a matrix here, we still have the logarithm, and we can still have its Taylor expansion, and we can still divide into 3 parts, 1, 2, and 3. And the third part is the easiest one. It is easily estimated by the special value of zeta function. So it is easy to see that this third part is bounded as x goes to infinity. And the first part is exactly what we want now, since this equals tau p over p to the 6 is equal to 2 cosine theta p over square root of p, and it is also equal to the trace of mp over square root of p. So this is what we are looking for. And the second part here, so this may be the hardest part, but generalized Merton's theorem, this is also proved by Kaneko, Kurokawa, and I last year. So by this theorem, this asymptotic is known to be minus 1/2 times log of x as x goes to infinity. So totally, we have the asymptotic of the tau p over p to the 6. So this is the proof. So the proof is very simple, and it can be applicable to many types of L function. The only hard part is the coefficient here. When I said about the Chebyshev's original case earlier, then it was just a positive 1/2. But in this case, it is negative 1/2, and that's the difference. And it reflects the property of automorphic L functions for individual automorphic forms. So it may be difficult to calculate this factor in a very general setting. But anyway, the proof of theorem 4 is done by this simple calculations. And here's another version of the theorem, theorem 5. We can adopt the same principle for symmetric power, symmetric squared L function. By doing this, we can do some, we can have some other types of biases. Actually, symmetric power is defined by like this. So this is the symmetric square of MP. It is the 3 by 3 matrix to e to the 2I theta p 1 and e to the minus 2I theta p. It's a diagonal matrix. So by using this matrix, we have the Euler product of degree 3. Then under the DRH for this symmetric squared L function, we can have the same type of result, and which is estimating the sum of tau p squared. So it is just looking at the tau function at the square of primes. And this is going to negative. So a bias of tau p square to being negative, that's what we proved from this. But when we change the views, then it can also suggest that a bias of the Satake parameters towards this region, because this is negative. So cosine is between 1/2 and minus 1/2. So it is suggesting that it has a bias towards this part. So it can be compared to the bias towards this part. So in theorem 4, we proved that it has a bias to this interval. Theta p is between 0 and pi over 2. But from theorem 5, it is suggesting the bias between pi over 3 and 2 over 3 pi. So it's a little different. So theorem 5 is not a refinement of theorem 4, but it gives another view, another way of looking at the distribution of Satake parameters. So that would be an additional result. That would be an interesting thing. But it may be interesting to consider other types of biases it will be done by thinking about the higher symmetric powers. So this is the last slide. Here is another application to the L function of elliptic curves. Okay, a global field. Let E be an elliptic curve over K. Then, as usual, we have the Hasse type L function, LSE. It is defined by the Euler product over good V and bad V. And then we can have the bias of AV by using the same principle. It holds under the DRH that you have a bias, which is the sum over AV over QV. QV being less than X. Then this is asymptotically equal to something multiplied by log of X as X goes to infinity. But when you assume the Burt-Singleton-Dyer conjecture, this part is expressed by the rank of E. So the bias depends on the rank. That would be an interesting phenomena on elliptic curves. So in particular, this value AV has a bias to being positive if rank is 0. So this coefficient is equal to 0 only when the rank is 0. When the rank is positive, then this is negative. So the bias is negative if rank is positive. And this red part is known for over function field case. So when the characteristic is positive, then the red part is already proved. So it holds unconditionally without purchasing into dia. Okay, this is the end of this talk. Thank you very much.
Thank you very much. Are there any questions or comments? If you have a question or comment, please raise your hand. すみません、これはオートモルフィックの場合のもいろいろ数値計算例はあったりするんですか？
数値計算例はオートモーフィックの場合にはまだやってないです。
ああ、そうなんですか。
アーブル拡大の最初に言った青木さんとの方では結構いろんな数値をやって、合ってるということが分かってきてるんですけれども、特にこの係数が具体的に青木さんが求めてくれたこういう形の係数があって、これがちゃんと合ってるのかというところも、この場合2分の1ですけど、いろんな数字がここに出てきたときに、ちゃんとこの挙動がぴったり合うということもいろんなケースで確かめているので、仮定付きの結果ですけれども、おそらく間違いないという感じはかなりあると思いますが。タウ P の場合にはまだやってないですね。タウ P の場合にも数値計算をやると面白いかもしれません。
どうもありがとうございました。大変面白い話でした。